Hello, Physics 1. Rotational kinetic energy comes next. And of course, we all know this song, You Spin Me Right Round. All right, so I thought we needed a fun start. Okay, so we're looking at section 9.2, rotational kinetic energy. So we know that this is all part of the relative kinetic energy associated with motion related to the center of mass, but it's not the movement of the center of mass. So for example, if we have a spinning disk, so this means it's spinning on axis here. So for example, we have a rigid disk rotating on axis. So in this particular case, it's spinning around, right round, baby, right round, but it's not translating in any way. So it does not have translational kinetic energy, but it does have rotational kinetic energy. So all of the atoms in this system have the same angular speed. Known as omega. So angular speed has to do with the time that it takes to make one complete rotation. So we can see here, when something spins around on a disk, it takes the same time for every part of that disk to make one complete rotation. So the angular speed is always the same. However, the velocity might be different because they might be traveling, or the speed might actually be different because they're going to be traveling different distances in the same amount of time. But the angular speed, which has to do with the length of time it takes to make one complete circuit of any size, is going to be the same. So, and this omega is measured in radians per second. We often see it written as 1/seconds. Okay, so as I said before, the linear speeds are different. And it depends on distance from the axis. So everything has the same omega, but you're going to get a different speed here as you would get here, as you would get here. All right. So building on this, angular speed. Omega is a measure of rotational speed. So basically, how fast is it going around? Right round, baby, right round. You're going to get sick of that joke, but it might help you remember this. So if an object makes one rotation, so that would be 360 degrees or 2 pi radians, in time t, omega is equal to 2 pi t radians per second. So yes, this is another area where you need to be careful as to whether or not you have your calculator in degrees or radians. So you'll need to make sure to read the problems carefully. T is the period, and this is measured in seconds, which makes sense with the 1/seconds for angular speed. An atom going around at constant speed at a distance r from the radius will travel a distance two pi r in period t, which can lead us to the velocity of that particular atom, or the speed of that atom. So I've not put a vector on it, so this is speed. Is 2 pi r, the distance around, divided by time, which is period t. This is equal to 2 pi t times r, which is equal to omega r. So now we can see, if we have the radius and we have the angular speed, how we can get the linear speed. So, and just be careful. Remember, omega is measured in radians, typically not degrees. Okay, so to understand rotational kinetic energy, I'm going to need to introduce a concept known as the moment of inertia. And it's just as epic as it sounds. Maybe. All right, so let's say we've got a 4-mass object and it's rotating. So let me draw some things on it. So we've got V1, so V1 is equal to omega r perpendicular 1. So r perpendicular 1 is here. V2 is equal to omega r perpendicular 2. V3 is equal to omega r perpendicular 3. And V4 is equal to omega r perpendicular 4. Change this into green, so r perpendicular 1 is here, r perpendicular 2, r perpendicular 3, and r perpendicular 4. And then it goes without saying, M1, M2, M3, M4. Okay, so this object is rotating. So the kinetic energy rotational is equal to 1/2 m1 times omega r perpendicular 1 quantity squared. So what we're doing here is we're using our standard expression of kinetic energy being equal to 1/2 mv squared, and we're trying to use that idea to then think about how we would go after rotational kinetic energy. And we're using our brand new expression for linear speed in terms of the angular speed. All right, so plus m2 omega r perpendicular 2 quantity squared plus the last two. All right, so rotational kinetic energy is equal to 1/2 m1 r squared r squared perpendicular 1 plus m2 r squared perpendicular 2 plus m3 r squared perpendicular 3 plus m4 r squared perpendicular 4, all of this times omega squared. So we factored out that omega squared from each one of these terms. So we don't know if the m's are the same. We can see by looking at the picture that the r's are different from the center. And we need something generalizable. Okay, so we have just identified a really important quantity. This quantity here is what's known as the moment of inertia. Conceptually, this is how much the object wants to resist rotation. Which makes sense. So if we think about it, the more massive something is, the harder it is to get it spinning. And we can see that encapsulated just even conceptually within the expression for the moment of inertia. So let's write out now explicitly what the moment of inertia is. So the moment of inertia is expressed using a capital I. So moment of inertia, capital I, is equal to the sum of all of the atoms times the distance from the center squared. And so we can use the moment of inertia to update K rotational. So rotational kinetic energy, and by the way, this is a general expression. We're going to talk about how to get specific expressions for different objects. So we will go through the methodology from whence these expressions are derived, and then I will just simply give you the expressions. So K rotational is equal to 1/2 the moment of inertia times omega squared. All right, so let's do an example. So what is the moment of inertia of a lithium molecule around the center of mass? Okay, so you need some more information. The mass of a lithium molecule is 1.52 times 10 to the minus 26 kilograms, and the average distance between nuclei is 2.9 times 10 to the minus 10 meters. Okay, so for two masses, that would be the mass of a single lithium atom. So for two masses, I is equal to m1r2 r squared perpendicular 1 plus m2 r squared r perpendicular 2. And distance is equal to r perpendicular 1 is equal to r perpendicular 2 is equal to d over 2. So our moment of inertia, which we'll need for this problem, is equal to m times d over 2 quantity squared plus m times d over 2 quantity squared, which is equal to 2m d over 2 quantity squared. Now we can plug and chug. 2 times 1.52 times 10 to the minus 26 kilograms times 2.9 times 10 to the minus 10 meters divided by 2. Our moment of inertia is equal to 6.39 times 10 to the minus 46 kilogram meters squared. So there we go. We had an object with two masses. We had two distances. We were able to use the most general expression for the moment of inertia to find it. All right, so let us continue. With another example. let's look at the moment of inertia of a bike wheel. My favorite kind of wheel. A bike wheel has all its mass in the outer rim. At radius r. So essentially what we're doing is we're neglecting the mass of the spokes compared to the much heavier mass on the outside of the wheel. So what is the moment of inertia about the center of mass? Okay, so the way to approach this is you have your bike wheel, and so you've got all these atoms, and they're all the same distance r from the center. And you're essentially, what you're going to do is you're going to make another assumption is that all the atoms of the bike wheel, you're just going to line them up together. You're going to say it's not that big of a difference between the front and end of the tire. And this is a reasonable assumption to make. So we have all the atoms of the wheel, and we need to add them up. Okay, so let's say m is the mass of one atom. I is equal to m1 r squared perpendicular 1 plus m2 r squared perpendicular 2 plus m3 r squared perpendicular 3, so on and so forth, on to, more atoms than I have paper. And then we know that all of these r's, these are all r's, are the same. So we could then say that the moment of inertia is equal to m1 r squared plus m2 r squared plus m3 r squared, so on and so forth. So I'm just using this picture here where we've got those capital R's. So let's simplify further. I is equal to m1 plus m2 plus m3 plus so on and so forth times r squared. And so what we see here, this is just the total mass. So I is equal to mr squared for a bike wheel. For a bike wheel assumes spokes are negligible. Okay, so now that we have an expression for a bike wheel, we can do an example and go after rotational energy. And so what we're going to be doing throughout this chapter as we learn about moments of inertia is we're going to slowly build towards how they're calculated. But as you will see, very precise measures of moments of inertia can be calculated for specific systems, but those precise calculations are a little bit beyond the scope of a Physics 1 class. And it's something that you do extensively if you take a classical mechanics class, where you just get problem after problem after problem of calculating the moment of inertia.